René Descartes. Descartes had been studying mathematics for some time, when, in 1631, he tackled the solution of a classical Greek problem. He proudly boasted that he solved it in 5 or 6 weeks. But it wasn't so much the problem itself that was important, but the entirely novel method of solution. What Descartes did was to set up the foundations of the system which we use today for the examination of curves and graphs, and which bears his name, Cartesian Geometry. The problem tackled by Descartes is known today as Pappus problem. We start with 4 fixed straight lines. From a point C, distances are measured to these lines at given fixed angles. The problem is to find all the positions for the point C for which this equation holds. The product of the distances d1, d2 must equal a constant multiple k of the product of the distances d3, d4. Pappus says that the point C may lie anywhere on some particular curve, and furthermore, that curve must be a conic section. But how to prove it? What follows is more or less Descartes' proof in his own words.
Since so many lines are confusing, I simplify matters by considering one of the given lines, and one of those lines to be drawn, as principal lines. To these lines I shall try to refer all others. Let x be the length of this line segment, and let y be the length of this line segment.
What we see here is the birth of coordinate geometry. Remember, the line segment y must meet the line segment x at a given fixed angle, so a pair of values for x and y will determine the point C uniquely and unambiguously. Descartes now proceeds to express every distance in terms of x and y. For example, the distance of C from the third fixed line is cy over z plus bcx over z squared, where c, b and z are fixed constants determined by the positions and angles of the 4 starting lines. Expressing all distances in terms of x and y and using the original equation, Descartes arrives at the following conclusion.
To find a position for the point C, we assign a value to x. Values of y corresponding to this value of x can be found by solving an equation of this form.
In other words, a position for the point C may be calculated without any reference to the geometry of the original problem. Instead, it's found by solving an algebraic equation. Descartes continues.
If we then take successively an infinite number of different values for the line segment x, we shall obtain an infinite number of values for the line segment y. And thus we can find an infinity of different points, by means of which the required curve can be drawn.
What's crucial about this solution is first the use of algebraic manipulation to solve a geometrical problem, and secondly, the complete generality of the method, which applies, as Descartes observed, equally well to problems starting with more than 4 fixed lines. In Descartes' words,
this method takes the best traits of geometrical analysis and algebra and corrects the faults of the one by the other.
It was the tremendous power of this method that was to reshape geometry. It quickly spread throughout the scientific community in Europe, where it got used, improved on, and helped to establish the language for modern science and mathematics. But producing revolutionary ideas in geometry was no guarantee of fame.